Yeah.
The answer is yes.
Yeah.
Okay, so, I talked about we do 5 units this semester, right?
Yeah.
Mhm.
And the first unit is limits. Okay, yesterday was kind of leading us into limits, but we're talking about limits. After that, I want to say units 2, 3, 4 probably. Maybe 2, 3, 4, 5. We talk a lot about derivatives. We go back to limits a little bit, but we talk a lot about derivatives. Second semester, we talk a lot about integrals. Okay, so those are our big 3 topics. Okay, you don't even know what most of those are. Limits is the only one that you maybe know.
I've heard of that.
I haven't
You
heard
know.
anything fun about it.
I don't know. There's some fun spots.
I hope so.
Okay, so understanding limits graphically and numerically. Limits are the backbone of understanding that connect algebra and geometry to the mathematics of calculus. In basic terms, a limit is just a statement that tells you what height a function intends to reach as you get close to a specific x value. Recall from pre-calculus that you evaluated 3 types of limits. Okay, we talked about limits a little bit, probably would have been first semester. Okay, we did a little bit with limits, not a ton, but we did some.
You had the parabola, and if it didn't go below the x-axis, then it was.
Or like the lowest point.
Yeah.
I mean, kind of. You can talk about what it's approaching. So, I'm not 100% sure if you're in the right spot or not, but you'll see here.
Oh,
Okay,
I think I'm thinking of boundary.
Oh yeah.
you might be. Okay, so 3 types of limits we're going to talk about. A right-hand limit, a left-hand limit, and then just a limit in general. The idea of a right-hand limit is as a graph is approaching a point from the right. Okay, so what is the graph is doing as we approach the point to the right? And where this really matters is in calculus you see a lot of disconnected graphs, where from the right the graph might go down here, but from the left the graph goes up here. And they're not connected, so we've got different limits to talk about. So proper notation, if you're approaching something from the right, the limit as x approaches, I'm going to use c from the right, and then f of x represents whatever function you're talking about. This is your proper notation. So the limit as x approaches c from the right of f of x. So you've got as x approaches c, the plus sign is after it because that's saying from the right, and that's under limit. And you've got f of x next to it, which just indicates the function. Okay, verbally, this is the limit as x approaches c from the right. Does that notation look familiar at all?
Yeah. What does the little plus sign mean again?
Okay, so the plus sign after the c is saying as we approach from the right.
Okay, so like from left it'd be minus.
Right, so the left-hand limit is going to be the limit as we approach a number from the left. So now I'm going to write the limit as x approaches c from the left means I put a negative after it. And so it's kind of like that plus and negative is almost like an exponent or something, but it's just a plus or negative, positive or negative. And so this is the limit as x approaches c from the left. So if you put a plus sign after the number, it's saying as we approach from the right. So as the graph is coming from the right, what y value is approaching? If you put a negative sign, it's saying as the graph approaches from the left, what y value you're approaching. If you don't put anything, and you just say the limit as x approaches c of f of x, that's just your general limit, and that's just saying the limit as x approaches c. So in that case, you have to look at from the left and from the right, are they meeting, and where are they meeting at? Okay? So the limit as x approaches c. And as I said, they have to meet. Okay, so I want to look at this rational function down here and start analyzing some of it, and really more than any kind of thing, kind of bring our vocabulary back together. And then on the next page, we'll actually talk about the limits, which that part may have to be tomorrow. But let's see what we can remember from pre-calc here. Okay, so use this equation for f of x and the graph of the function to analyze completely. So we're filling in this box, answering all these questions. Factor and simplify. So this function factors. You want to start easy? Let's go with the x squared minus 9.
X minus 3.
Yeah. No. Yeah.
Factor out. Wait,
Um,
you can't.
Aiden's close, but not quite.
Oh, wait.
Wait a minute.
No. Close.
X plus 3 and then x minus 3.
Oh.
Aiden said x minus 3 twice. But x minus 3 twice would give me a positive 9, but I'd also have a middle term of minus 6x. So difference of squares, right? Square root of x squared is x, square root of 9 is 3, and then it's a plus and a minus because that way the middle term cancels. That numerator, it factors.
Multiplies to 9 and adds to negative. Multiplies to negative 9 and adds to negative 8.
Okay. So she's going product of AC there, isn't she? Okay, now, I would argue that you could, I don't know. I always like you guys to try it, and I always get, denied.
Slip and slide.
I like that.
No, not even slip and slide on this one. I mean, yes, you can slip and slide, but just kind of a trial and error. Like, if we just look at the 3x squared, what are going to be these two pieces if that's a 3x squared? What times what are we going to use for 3x squared?
1 and 3.
1 and 3. And so 1x and 3x. I'm going to make it 3x and x just because my brain does that. This is just kind of a guess and check type thing. 3x squared. 3 is just 1 and 3. So I know it's going to have to be 3x times 1x. Fair enough? Now, just look at the end here. What are my options for multiplying to be 3? 3 and 1 again, yes? Now, here's the deal. You've got a 50-50 shot. Is it 3 and 1 or 1 and 3? And this is where it's a guess and check in terms of, okay, I'm going to look and see. Don't write that down yet. I'm just penciling it in. If I put 3 and 1 here, look at your outsides. 3x times 1 is 3x. 3 times x is 3x. 3x plus 3x is going to be not 8x, right?
Nope.
So my 3 and 1 need to flip. So now what if I do 1 and 3? Here's another thing, guys. Nothing would have simplified if I would have had, the 1 there. 3x times 3, if I look at my outsides, is 9x. 1 times x is 1x. Can 9x and 1x make 8x?
Yeah.
Yeah, they can, right? How do they make a negative 8x?
The 3x plus 1 is positive, and then x and 1.
Yeah, because in my brain I was saying I need a negative 9x and a plus 1x, right? So to get a negative 9x, it's 3x times 3. That needs to be negative 9x. 1 times x needs to be positive. And did that work for my negative 3 here? Positive 1 times negative 3. Now, slip and slide, product of AC, are those still awesome methods? Yes. Am I saying you can't use them? No, not at all. As calc kids, I like to try and challenge you when there's not a lot of options to try this one. Okay? It said factor and simplify. What do we notice?
Cancel them out.
Yeah, we do have a canceling here, don't we? Okay. So, okay. Coordinates of the hole. There's a hole. How do I know there's a hole?
Okay. Oh, there's
Not looking at the graph.
Oh.
Looking at,
You have the ones that cancel.
yeah. When you have a factor on top and bottom that cancel, what's that factor represent over here? That represents that there is a hole. A hole where? If this is the factor x minus 3, I always say set equal to 0, so there's going to be a hole at x equals 3. Yes? Now, it technically says it wants the coordinates. So when we talk coordinates, I'm looking for an ordered pair. Options. I could look at the graph. Now, is this making sense, folks, that there's a hole there? I said there's a hole at 3. Guess what this is at? 3. But I'm trying to remind you of, we don't always have the graph we're looking at. Holes don't show up great on the calculator. How do I get the y coordinate? I just plug it in. You could plug it into the original. You could plug it in right here. This one seems easier to me. 3 times 3 is 9, plus 1 is 10. Over 3 plus 3 is 6. 10/6. I'm going to write 5/3. Okay. AP Calc wouldn't care, though. They'd take 10/6.
You don't have to simplify.
Nope. I'll talk about some really crazy stuff you don't have to simplify eventually. Basically, if it's equivalent to the final answer, you don't have to simplify it. If you hit a point on the free response, multiple choice, obviously, it'll be simplified. But on a free response problem, if you hit a point where it's just calculations from that point forward, I mean, something, you could leave, that as an answer.
You couldn't do that with
Just
SATs,
because
did
it
you?
breaks down.
Yeah, and because here it's just a matter of doing computations. And now, that's hard for me to leave. But technically, I should recommend you leave it because what can happen if you continue from here?
You can mess it up.
You can mess it up. So they'll argue that there's an advantage to leaving it here because you can't, if this is right, and now on my next step, you do something, you say 81 or 82/6, you've just lost a point.
That's fine.
So, I know, random side note.
Do we have to
Okay.
simplify your tests?
Not necessarily. I mean, I don't count off if you don't. So, I always encourage it, but yeah. I don't feel like since the AP Calc test doesn't require you to, that I, can require. Okay. Now, real quick, a little bit of vocabulary I have written in that I just looked at. This hole. It is, do you remember the word discontinuity?
Maybe.
We talked about first, probably like chapter 1 in pre-calc. Okay, the hole is a discontinuity because it's a break in the graph, right? I can't keep drawing my graph there without picking up my pencil. So it's a discontinuity. When we talk about what type of discontinuity, it could either be referred to as a point discontinuity, which is new in calculus, or do you guys remember talking removable and non-removable?
Yeah.
This is a removable discontinuity because you can remove that point and fill that hole back in. So a little bit of review there. Oh my gosh. Domain. What do you remember about domain? X. So we're going left to right here. Okay. So where does my graph start on the left?
Negative infinity.
Negative infinity, yes. And we're going to go interval notation. Negative infinity. Infinities always use parentheses. Okay. My graph goes to negative infinity. It's going, it's going, it's going. How far does it go?
2, 3.
It's going to this asymptote.
Yeah.
And that asymptote is at Negative 3.
Negative 3. I got
Okay. Parenthesis or bracket?
parentheses, bracket. I don't know.
Why did I write a parenthesis?
Because it's negative, not touch.
No,
I don't
what?
know. It is touch.
Is my graph ever going to touch negative 3? No, because it's an asymptote. Okay? Okay. And then I'm going to use the U for union.
Oh, I forgot about that.
Where's my graph pick back up? Or actually, you know what? I just have a comma here in my notes now that I look at it. But where's my graph pick back up? The other side of negative 3, yes? Parenthesis or bracket? It's not touching it because it's an asymptote. Okay, how far does it go?
Infinity. Oh,
Do we have a break at positive 3?
yeah.
We do. Positive 3, because there's a break. Parenthesis or bracket. Parenthesis, it's a hole, it does not touch it. Where's my graph pick back up?
Other side 3.
Other side of 3. How far does it go? Infinity.
Yeah.
Ooh, that was really bringing that information back, okay? Now, the fact that there were breaks at 3 and negative 3, we knew that because any place the denominator equals 0, which is 3 and negative 3, that won't be in your domain, okay? The fact that x plus 3 is here in the denominator, that means that at negative 3 there is a vertical asymptote. You remember that? Okay? Awkward place to stop, but it is what it is.
So why did we use commas, not union?
You can use either or, I think.
Okay. I just didn't know if there was like a specific reason.
I know, I'm trying to remember, unless there's a reason we don't use it in domain that I don't remember. But, yeah.